Hi everyone, my name is Dario from Sapienza, University of Rome. And in this short presentation, I'm going to talk about our security analysis of split learning. This work has been done in collaboration with Stevens Institute of Technology, New Jersey, USA. In our work, we aimed to verify two main properties of split learning. The first is the security of split learning against a malicious server. That is, if a malicious server can or cannot infer meaningful information on the client's data during the training. The second property is the security of split learning against a malicious client. That is, if a malicious client who participates to the training can or cannot leak information on the data of the other honest clients. In the next few slides, we will see how split learning can be violated on both these adversarial scenarios. Let's start talking about the malicious server scenario. Here, the server is malicious and wants to recover the private training instances of clients from its mesh data. The server tries to do this during the training process, so while the clients are learning the distributed model. We assume that the attacker has no knowledge of the client's network F. It doesn't know anything about its weights. Here, the only assumption is that the server has a general knowledge on the distribution of the private training sets of clients. For instance, if the clients are training a face recognition model, the attacker knows that the client's training sets are composed of pictures of human faces. The core idea behind our attack is quite simple. The only thing we have to understand is that even if the server doesn't know anything about the client network F, the network F is trained using the gradient received from the server. Therefore, the server can force F to learn any function by just providing suitable gradient to it. In this direction, the server can force F to learn a function that leaks information about the raw input data that is used to cast the mesh data sent during the training. For instance, the server can force the network F to learn a function that can be easily inverted. To carry out the attack, the malicious server uses three networks. The first two networks are used to build an autoencoder, which is trained with a dataset that follows a similar distribution to the client's private training sets. Here we can see f tilde as an encoder function that maps the data space into a feature space. In the same way, we can see the inverse of f tilde as a decoder that maps back the feature space into the original data space. Essentially, the decoder aims to force f tilde to learn a feature space that is invertible. Then there is a third network, D, that is a discriminator, which is trained to distinguish between the output of the client's network F and the output of the network f tilde. This network is then used to cast the gradient for the client's network F during the training and bring it in an insecure state. In particular, we use the discriminator D to implement an adversarial function for F. That is, we train F to fool the discriminator D. More pragmatically, we cast a gradient that trains F to produce an output that is indistinguishable from the one of f tilde, according to D. This slide should give a better intuition on the process. At the start of the attack, we have that f and f tilde map the data space into two different feature spaces. Then we use the discriminator to train f to produce an output that is as close as possible to the one of f tilde. After a certain number of iterations, the feature space learned by f overlaps with the one defined from the f tilde. Once that is happened, we can use the inverse of f tilde to map back the smash data sent by the client during the training and recover good approximation of the original private data. Here are some results. In our paper, we tested different image datasets. As can be observed, with this attack, a malicious server is capable of violating clients' privacy by producing good reconstructions of their private data at the instance level. This would allow the server to leak complete private sets by just inverting instance after instance. This server-side attack applies on almost all the variations of split learning. For instance, it applies also in the U-shaped form of split learning, the one with the private labels. Indeed, this attack can apply even if the client controls the computation of the loss function. Indeed, it's enough to ignore the gradient received from the second split of the client and perform the attack as we saw before. Similarly, it applies on other variations, for instance on split learning when the synchronization among the weights of the clients is made with feathered learning. And it applies also on vertical split learning. Indeed, the core idea is that this attack remains applicable as long as the server controls the learning process of the clients. This happens always in split learning. For similar reasons, this attack is also capable of evading defensive techniques such as the distance correlation minimization. For more details on this topic, please check our paper. Let's glance also the client-side attack. Here the attacker is one of the clients who are participating to the split learning product. The attacker wants to infer meaningful information over the private training sets of other honest clients that are participating to the training. This attack requires no assumptions. That is, the malicious client has no additional information on the private sets of other honest clients. However, in this case, we can trust the server. This attack is essentially an extension of the GAN-based attack devised for feathered learning by Hijacking et al. In particular, this attack works on the U-shaped form of split learning. Here, the malicious client trains a GAN generator to reproduce the distribution of a certain class owned by one or more honest clients. To train this generator G, the client uses the distributed model as a discriminator by just altering the computation of the loss function on the client side. However, being an adversarial loss, the malicious client must also avoid the server's network hash to modify its weights while training the generator. To accomplish this, the attacker resorts to a gradient scaling tree that reduces the magnitude of the gradient for S and prevents it to change its weights during the distributed backpropagation. Then, once received the gradient from the server, the attacker scales the gradient back and uses it to train the generator. Once that the generator G has been trained, the attacker can sample data points that follow the same distribution of the target class. This allows the attacker to leak information on the private sets of other honest clients. Thanks for your attention. Please check our paper for more details and additional results. Our code is available on GitHub. Forecast and try to extend or prevent our attacks. Thank you.